Welcome to another solution with a physics tutor. In this video, we'll explain and solve problem 5 from chapter 11 of Giancoli's 7th edition. The problem reads, a fisherman's scale stretches 3.6 centimeters when a 2.4 kilogram fish hangs from it. A, what is the spring stiffness constant? And B, what will be the amplitude and frequency of oscillation if the fish is pulled down 2.1 centimeters more and released so that it oscillates up and down? So our first thoughts here are to draw the scale. So the way a spring scale works, it is a spring. And in this case, we're going to suspend it from something upwards. And this is the length of our spring. We don't really know what it is, but we're going to say this is our unstretched spring. And then the fisherman puts a fish on it, and that causes the spring to stretch downward. So as that spring stretches downward, it extends past that initial equilibrium position to give us a new equilibrium position because we have our 2.4 kilogram fish attached to it. And we are now in a new equilibrium position. So this is unstretched equilibrium, and this is our stretched equilibrium due to mass of the fish. Okay, and we know from the problem that the stretch is in fact 3.6 centimeters. Okay, so in part A, what is the spring constant K? Okay, that's what we're solving for. So what do we know? We know the mass attached to the spring is 2.4 kilograms, and we know that the displacement of the spring from its initial equilibrium position is 3.6 centimeters, which we can quickly convert to meters. So there's 100 centimeters and 1 meter to give us 0.036 meters. We also know that the fish is applying a force on the spring equal to its weight force. So we're assuming we're here on Earth, so G is 9.8 meters per second squared. And of course, K is unknown, and that's what we're solving for. So if we were to imagine that we had a positive x and negative x, so this is our x-axis right here going from up and down on the page with positive up and negative down, we can write a sum of forces in the x direction using Newton's second law. We can say that the sum of forces in the x direction is going to be the spring force upwards, so F spring upwards, minus the force of gravity down, because gravity is downwards, and that's going to equal the mass of the fish times its acceleration. Now, recall at EQ, the equilibrium position, A equals 0. And we're looking at the fish at the equilibrium position. So we can write that the spring force minus the force of gravity is equal to 0. Now the spring force is actually defined as negative kx, and our gravitational force will be the mass of the fish times g, okay, and that's equal to 0. And now we can solve for k. This is a lot like what we did in problem number 2 when we added the driver into the car. Okay, so if we solve this for k, we can have negative kx is equal to, bring this to the other side by adding mass of the fish times g. So that k then will be equal to negative mass of the fish g over x. So in this particular case, k is going to be equal to the mass of our fish, 2.4 kilograms, times g, 9.8 meters per second. That's literally the weight force of the fish, divided by our displacement. We're in the downward direction, so our displacement is negative 0.036 meters. And we will put a negative sign out in front of that. That's that negative sign right there. And we plug those numbers into our calculator, and you should come up with something like 653.3 Newton meters. And then we will round that to 2 significant digits to give us 650 Newton meters for the K value of our spring. And that is the answer to part A. Okay, this is our part A answer right here. In part B, they have a different question. They want to know, what is the amplitude and frequency of oscillation if we pull the fish down a distance of 2.1 centimeters and let go. Okay, so what we're going to be doing is we're going to be taking hold of the fish and pulling him down from his equilibrium position, 2.1 centimeters, and letting him go. That means the fish is going to oscillate up and down around this equilibrium position. Okay, the maximum distance it will be away from that equilibrium position will be 2.1 centimeters. Based on the conservation of energy, it's never going to get further away from the equilibrium position than that initial distance that we pull it downward. Okay, so that means this is the amplitude. Okay, so amplitude equals 2.1 centimeters. The fish can never get any further away from its equilibrium position than the distance we initially displace it. So there's one of the answers for part B. And now we need to solve for frequency. Well, we know that frequency is the inverse of period. So therefore, frequency is 1 over 2 pi times the square root of k over m. This is the inverse of the period formula. We know what k is, we know what m is. We can solve for the frequency. So in this case, the frequency would be equal to 1 over 2 pi times the square root of 650 Newton meters divided by the mass of our fish, which is 2.4 kilograms. And we can just plug these numbers into our calculator, and we can solve, and we come up with 2.62 hertz, or oscillations per second, which will round to 2 significant figures to give us 2.6 hertz as our final answer for part B. So the answer to part A, 650 Newton meters, is our spring constant. The amplitude for our fish's oscillation once we pull it down 2.1 centimeters is in fact the initial displacement that we give it, and it will oscillate with a frequency of 2.6 hertz. Hopefully you found this explanation useful. If you did, please like and subscribe, and as always, enjoy your physicsing.